Okay, we'll get started. I don't have any fancy graphics for you today for the grades. I started to put together something, but I stopped. So I'll just tell you right now, I believe that the exam average was a 77.3. So it was pretty good. The exams are right there on that table if you need yours. We only meet 6 times before the final. Okay, so we have 3 weeks of class left. And what I've been thinking is I'm probably going to give the final exam as partial take-home, partial like in class. I'm thinking the take-home part's going to be like 20%. I mean, just it's not a lot, but it's still so I can get you to do a couple of problems outside of class that'll allow me to get through everything I want to get through on the final. The final is going to cover mostly Chapter 8. I mean, pretty much from 8.2 on through whatever we get through in the next 6 meetings. So, yeah, that's where we are. One thing, at the end of class last time, I had a little issue where I'd run into this problem and things weren't working out, and I went back and looked at it, and everything was okay. The issue was that the theorem guarantees us, if you go back and look at your notes, it guarantees that if we go out to a certain place in the series, we're guaranteed that our error is going to be within a certain margin. The arithmetic that we did when I tried to show it with the computer, it appeared that it had happened before that. But the theorem just tells us that there's a point we can guarantee. It may happen before it, but it actually gives us a point that we can go to. If it happens before, great, but it gives us, I guess, a stopping point. So there was really not an issue with it. It just, the theorem had an inequality in it. And whenever you have something like that, then if you say this side's bigger than this side, that means there could be stuff in between. So it could have happened earlier. All right, I just wanted to not leave that as an open thing. All right, so what we're going to do today, we're going to do 2 more tests that we have in 8.4, and then we're going to move on to 8.5. So the first test, or the next test, I should say, is called the ratio test. And this test is going to be used a lot. I thought I just silenced my phone. I did. Why did it beep? Was that someone else? Was that your phone? No. Okay, so when we get into 8.5 and 8.6 and 8.7, we're going to be using the ratio test quite a bit. So we need to be familiar with it. Here's what it says. It's on your sheet, right? If you're given a series, and this series, it does not matter if it's alternating or not. So this works for any series, which is a good thing. If we're given a series, we're going to take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And we're going to see if we actually get some sort of answer. So what we're doing is we're taking the series. Remember, this is a1 plus a2 plus a3 forever. And remember, this thing keeps going, right? Forever. But if we go out to the nth term, and we look at the nth term, we look at the n plus 1 term. So we look at these two, and we write them down in a ratio, and take the absolute value, and then take the limit as n goes to infinity. We try and figure out what this ratio is approaching. And here are our conclusions. If L, that's the limit that we find, is less than 1, the series converges. If L is greater than 1, the series diverges. And if L equals 1, the test fails. All right? So those are going to be our results. So we just need to be able to run this ratio test. Do a little limit. We'll probably need some L'Hopital in here. Take an absolute value, see what happens. So let's go with the first example. And what does it say on your little cheat sheet there about when you should use the ratio test? Oh, do y'all have that still? That cheat sheet? Okay. Yeah, so, whenever you see factorials or whenever you see things raised to the power of n, you should be thinking of this test. So our first one, let's do n to the third power over 5 to the n power. So by looking at this real quick, what does this look like to you? I mean, what type of series does it kind of look like to you? Kind of looks geometric, right? Because you have that 5 to the n. But the problem is you also have an n cubed, and that kind of makes it not geometric. Now, we could try a comparison test. We could try and compare this to a geometric series. And there's all those other tests that you have, right? Integral test, nah, we wouldn't want to integrate that. So let's go to the ratio test right away and just see what happens, all right? So if I run the ratio test, what I'm going to do is I'm going to take a limit. I'm going to let n go to infinity, take the absolute value, and then very, very carefully, I need to create this ratio. It's going to be a sub n plus 1 over a sub n, right? That's what I'm going to be doing. So what does it mean when I say a sub n plus 1? I'm going to take this formula, right? This formula right here, that's a sub n. But instead of plugging in n's, I'm going to plug in n plus 1's, right? Okay, so I'm going to put that up here. And then below it, I'm going to put a sub n, which is just going to be this right here. So here's what it'll look like. N plus 1 cubed over 5 to the n plus 1 over n cubed over 5 to the n. Do you all agree that that is a sub n plus 1 over a sub n? Yeah? Okay. Now we have what we call a complex fraction. It's just a fraction over a fraction. So remember, if you take a fraction divided by a fraction, it's the same as multiplication of the reciprocal, right? So I'm going to go ahead and take n plus 1 cubed over 5 to the n plus 1. I'm going to multiply that times the reciprocal of the denominator, which would bring that 5 to the n up top and the n cubed on the bottom. That's still good? Bless you. Yeah? Okay, now just a little algebra, some properties of exponents. We've kind of done something like this before. I'm going to take the 5 to the n plus 1 that's in the bottom right here, and I'm going to rewrite that as 5 to the n times 5, or 5 to the 1. Do we need the 1 there? Do you want me to write it? I'll write it there. That's the same, right? 5 to the n plus 1 is 5 to the n times 5 to the 1, and then times n cubed. And do you see why I did that? These 5 to the n's are going to cancel out. Okay. So we made a little progress here. Let's kind of reevaluate that limit and just see where we are. Limit n goes to infinity. And let's see, I've got on top n plus 1 cubed, right? That's the only thing left. And on the bottom I have what? 5n cubed. All right. Now, a quick look at that limit. If I let n go to infinity, it's obvious that's infinity over infinity. And so I can use L'Hopital's rule. Now, I also had infinity over infinity here, right? Like that's infinity times 5 to the, well, that would be infinite and infinite and infinite. But would you want to do L'Hopital on this? Probably not, right? Because you'd have to do like a product rule on the top, product rule on the bottom. It's a mess. Canceling out makes things a lot easier. So let's go ahead and run L'Hopital on that. And I think just, well, yeah, I'll just run it right now. L'Hopital, n goes to infinity. Oh, about the test. Obviously, I had to grade that under time constraints, right? I was trying to get those posted. I actually did not start grading them till 1:30, and I had both classes graded by 3. So I went fast through those. So if you have any questions on why I took off something, or you want to kind of argue your case that you feel like you deserve more points, or maybe I just missed something, okay? Don't edit your test. Don't do anything. Don't add anything to it. But just come sit down with me and I can kind of run through it with you. All right? Okay, so L'Hopital. I'm going to take derivative of this. I chose not to expand it. I was thinking about just doing n plus 1 times n plus 1 times n plus 1 and just expanding it out first before I took the derivative. But I'm going to choose to not do that. I'm just going to do chain rule on it. Isn't that the derivative of the top? And that's the derivative of the bottom? I still have infinity over infinity, don't I? Yes? But what's happening is every time I take derivative, the power's coming down, isn't it? So let me try L'Hopital again. Okay, derivative of the top, so 6, and then n minus 1, right, over 30n. Still have infinity over infinity. And let me go ahead and distribute that through. That's 6n plus 6 on top. One more time with L'Hopital. Limit. N goes to infinity. 6 over 30. And that's a constant now, isn't it? So 1/5. Okay. What's our conclusion? This series converges because this is less than 1, right? So since it's less than 1, this series converges. We don't know what it converges to. We just know it converges. Yes?
Never mind, it was a dumb question.
No? Go ahead. What?
I thought you could factor out a 1/5 and then just rewrite it as n plus 1 over n, then take the limit of the...
Where are you talking about? At what point? At the very beginning? Out here?
Yeah.
Like pull a 1/5 out right away?
Yeah, and then just rewrite it as n plus 1 over n cubed.
Oh, okay. I see what you're saying. N plus 1 over n, both of them cubed. Like that? Is that what you're saying?
Yeah,
Yeah, you could do that.
easier?
Well, I thought that was pretty easy.
Really?
Right? I mean, taking the derivative a couple of times of polynomials isn't really, but yes, you could do this. Because here, if you do the limit, you can go here, you'd have to do L'Hopital once. You would get a 1 here, right? 1 cubed is 1, then times 1/5. So you get the same thing, yes.
So you're saying you know converge, you're treating this like a geometrical series?
No, because remember, we ran the ratio test, right? And that limit that we took, this right here was the L that we got, right?
So that's a little bit.
And for this test, if that's less than 1, it converges. Good? So yes is the answer. Yeah. All right, let's try something else. I'm only going to give you like 3 examples of this because we're going to get plenty of practice with the ratio test. The next one, let's do one that alternates. How about that? How about -1 to the n times n factorial over n to the n. Now, we don't have to have a factorial to use the ratio test. But when you see factorial, you should be thinking ratio test because of what's about to happen. All right, here we go. Ratio test. I don't care that it's alternating. And why is it not going to matter? Because the absolute value, right? Okay, so I'm going to set up my ratio. Now, a sub n plus 1 over a sub n. So let's plug n plus 1 into all of these. And be kind of careful when you do this. We're going to have -1 to the n plus 1 times what? N plus 1 in parentheses, right? Factorial. Do not write n factorial plus 1. Those are not the same things. All right, don't write that. That's incorrect. It's n plus 1 factorial. And then over, careful here, n plus 1 raised to the n plus 1. And now the bottom's the easier one because it's just you just have to copy that down again. So -1 to the n factorial over n to the n. And now whenever I have the complex fraction, I'll always do that flipping over now. So I'm going to go ahead and flip. I have negative 1 to the n plus 1 times n plus 1 factorial over n plus 1 to the n plus 1 times, let's see, what's on top here? On the top one I flipped, remember? So n to the n up here, and then on the bottom, negative 1 to the n, and then n factorial, absolute value. Now, the absolute value comes into play right now, because I'm going to start trying to clean this up. And no matter what this is, right, whether it's positive or negative, I'm going to wind up taking the absolute value of it, and the absolute value of 1 or negative 1 is just 1. So it's basically gone, right? Same thing with this one. So what I'm going to do is just basically ignore these completely and just act like they're 1s. I'll leave the absolute value there, all right, but just understand that what we've done is just kind of ignored those because of what would happen with the absolute value. I'm also going to play some little games here with my factorials. We already know that n plus 1 factorial can be broken down a little bit, right? That can be broken down to be, what, n plus 1 times n factorial? That's what this one is. And I stopped at n factorial because I have it on the bottom. So I'm going to want it to cancel out. What else is also on the top? If I brought n to the n is still up here, okay? So that takes care of the numerator. Denominator might need a little more room. How about if I rewrite this as n plus 1 to the n times n plus 1 to the 1? Isn't that the same thing? Again, using properties of exponents, same base. Put those together, add the exponents, you get back to this. And do y'all see why I did that? You see what's going to happen? Okay, so my canceling that I'm going to get here, the n factorials are gone, and n plus 1 cancels with this n plus 1. I still have n to the n on top over n plus 1 to the n. Agreed? So here's where we are. Limit, n goes to infinity, absolute value of n to the n over n plus 1 to the n. We still are getting like an infinity over infinity, aren't we? Don't want to use L'Hopital right now because I don't want to take derivative of n to the n. And I definitely don't want to take derivative of n plus 1 to the n. So maybe we can use kind of that idea that they're both raised to the n, right? Okay, since they're both raised to the n, I could do this. And I get what? N over n plus 1 to the n. Oof, okay. This is looking a little bit messy now. What happens as n goes to infinity? Tell me about what happens in here. What's that inside piece going to? Infinity over infinity. So if you did L'Hopital on just this piece, right? If like that was its own problem, what would that go to? 1, right? That's going to go to 1. So we have the inside piece here is approaching 1. And what's the exponent approaching? Infinity. And this is an indeterminate form, right? Anytime we have 1 to the infinity. Remember, we're not saying that this is ever 1, right? We're not saying that that's 1. We're saying it's approaching 1. That's approaching infinity. Indeterminate form. So what I'm going to do now is I'm going to kind of step away from this for a second, and I'm going to do some scratch work here on the side. I'm going to drop the absolute value because these are all positive numbers, so I don't care about absolute value anymore. And I'm going to try and remember from Cal 1 how I dealt with limits when I had this indeterminate form. And the way we did it was to say that this is y, and then take natural log on both sides. And the purpose of that is to try and be able to drop the n out in front. So I'm going to call this limit y. So remember, everyone, we're trying to figure out what y is. But I'm going to take natural log here,